There he is. The next speaker is Georgios Bakirtzis, and please go ahead.
Can you hear me?
Yes.
All right. Hello, I am Georgios Bakirtzis, and I am a cyber-physical systems safety and security researcher at the University of Virginia. I'm going to present our application of what I would consider basic categorical concepts to the design and hopefully in the future assessment of cyber-physical system models. So I would position this talk in the applied fraction of category theory. This work was conducted with Christina Vasilakopoulou and my advisor, Cody Fleming. Specifically, we're going to concern ourselves with pictures like the one here, which you will see hopefully by the end of this talk, how it depicts unmanned aerial vehicles, behavioral models of unmanned aerial vehicles in the wiring diagram category. And that's the first result of the paper. The second being how we can hierarchically decompose using category theory these images to candid implementations while keeping traceability between the two, which is a huge issue right now in systems theory, I would say, in systems engineering. So what are cyber-physical systems? Cyber-physical systems are often systems that incorporate digital control with physical processes to operate in the environment. Such systems include what is called like the smart grid, so not necessarily power plants, but the architecture that distributes power these days. It includes also autonomous vehicles, which probably have the highest visibility research out of cyber-physical systems in the public, mostly how they fail. But we have actually bigger systems like the air traffic control system is nowadays a cyber-physical system. And then we also have smaller ones, which are biomedical applications of cyber-physical systems. You could easily imagine that these systems could fail. And when those systems fail is not the same as traditional IT systems. You could see that if an IT system fails, you could have an economic collapse, perhaps. But with these systems, we've seen it. It has happened. We can even have loss of life. So we require models of these systems in order to make sure that they provide enough evidence that they're going to behave correctly once they're deployed. So these models have been enumerated by the cyber-physical systems researchers. You're welcome to check that site out and see, because it has a lot of images that I think would appeal to category theorists. But this concept map is the current ontology of things or stuff that must be taken into account for designing cyber-physical systems. In this concept map, you could spend PhDs at each of those leaf nodes. Let's say people spend 7 or 8 years in how do we design control for these systems. And then you also have particular domains that those things exist. So my particular application is unmanned aerial vehicles, but someone else can spend years on energy. I found it very important that we're able to connect those model views. Right now, this is done informally. People really specialized in one of these leaf nodes, and then they informally say they're connected to each other. But the mismatch between the leaf nodes when it comes to modeling those systems can actually cause something to even crash or explode. So we want to be able to have formal traces between those systems. So before even I learned about category theory, I had this notion of mission, behavior, and architecture. And I wanted to think about the problem about how do we match those different model views and what do the arrows mean? And because of the intertwined nature of digital control with the environment, the only way to actually make sure that we have correct operation is to connect behavior and architecture, and also think about the expected behavior of the system in one model. I found that this was wrong, and this was brewing for years in my work, but this became apparent when I was working with Christina on the formalism, because what does it mean to have behavior and architecture? Well, once we look at wiring diagrams, it's going to be more clear, but in my opinion, we can see that there's behavior and architecture at each level, except maybe the requirements. So the system function has a behavior and architecture. The implementation of that system has a behavior and architecture. And then the requirements are contracts or constraints over those functions and implementations that percolate below. Category theory gives us the mathematical machinery to understand how different models are connected and in what way they're connected. And I think in the future, if we do model things with category theory in this domain, we can provide guarantees and consistency between abstraction layers. So when an electrical engineer says something about the system function of the system, that is not the same as a mechanical engineer saying something about the system function of the system. So how do we conglomerate all those views in one view? So my aim and our aim as a group right now researching this is to build a metatheory of compositional systems theory to combat and basically reduce semantic ambiguity, because I don't think you can remove semantic ambiguity. So how does an individual model view compose to produce a set of known behaviors? To manage complexity of models, how do we solve the problem of large models without being able to abstract properly? So in practice, models are not the small models we show in papers. In practice, models have nodes up to the 800,000 entities. And then the final thing is the intractability, which basically is the dual of how do we relate those different model views? And I believe category theory will lead to unification and scalability. We can formally represent processes interactions, which I consider the dynamic view of the system. And we also can have relational ontologies. We can give us this traceability between different domains. So let's see how a systems engineer might think of the design of any system, not just cyber-physical systems. The most common language in America, Modelica in the EU, is SysML. And SysML has this structure. It has behavior diagrams, which also have a subclass of diagrams that you might choose to use. It has requirements diagrams, and it has structure diagrams. Behavior and structure here basically define what we said before as function and implementation. And even though we say behavioral diagram here also has a behavior and architecture. So you don't have to use all those to design a system. You can choose, for example, to use only activity diagrams or only state machine diagrams, and then you can choose something for your structure. Let's say you only use block definition diagrams, and then there's only one diagram for requirements. The point being is that these arrows don't mean anything because you have to do those individually. And you have no way of saying that if I created, let's say, a state machine diagram in my SysML modeling tool, that it has any congruency with my block definition diagram. So I believe, and we have early indication, that wiring diagrams can actually do this if we build modeling diagrams on top of them. We haven't shown in this paper how behavior requirements connect in the form of contract-based design, which is already done in control, but I want you to trust me on that. And then we have, however, shown how a controls model and a state machine representation can be represented wiring diagrams, and then how you can have a connection between that part of your wiring diagram and your structure or otherwise implementation diagrams. So what are wiring diagrams? Wiring diagrams were presented in the early 2010s by David Spivak and other collaborators. And it's a monoidal category, and the objects are pairs of sets. And I want to say something maybe a little bit controversial, I don't know actually, is that whenever I've discussed category theory with engineering professors, they always get caught up with the fact that you always need to reflect things on sets for engineers to get them. And that's something that you might want to keep in mind if you want to communicate with that part. The morphisms are functions, which basically define the input and output of that black box of Y, let's say in this case. And then it has a tensor that shows parallel placement. What is the good thing about this? Well, wiring diagrams can actually, with these three things, model reactive systems, feedback, and real-time computation, all of which are really important in cyber-physical systems. Wiring diagrams have a strong relation to dialectical categories, lenses, and compositional game theory, which we've seen a lot of. And there's investigation there how they relate particularly. The two functions that define the morphism in this category are special, namely they're built from projection, diagonals, and switches. So how do we model systems as algebras? Well, we can just literally start building things the same way we build them in engineering, except we have to sort of reverse engineer that they actually compose, because when engineers put two boxes and a wire together, it doesn't mean that they actually compose. So here we need to make sure that the bottom left picture actually makes sense in a physical implication. So when we say like, oh, we have everything real numbers, they don't have to be real numbers, of course, but we have to make sure that whatever comes out of that system is gonna be in agreement with phi in and phi out. So generally, what do we do with wiring diagrams? I believe that we are addressing emergence. I did see Jules' talk the other day that put some doubt into this, but I think that if we do things right, and if we do things with expert input in this case, we can address emergence, which is one of the biggest issues when you're modeling systems. How do we address emergence? Well, by actually knowing exactly how things relate to each other, by having this composite system functor, and by having those parallelizing operations and making sure that what we're writing down actually makes sense mathematically, but also like in the laboratory, that would be good. And I'm using here emergence in the sense of check length. I don't use it in the general sense of emergence. So Checklin takes the position that a level of complexity is characterized by properties that do not exist at lower levels. And that everything, if we do it hierarchically, then that's okay for emergence. Other people disagree with this. So what is the main result of this paper is actually this particular example of a UAV, where we have this picture that looks and feels the same as SysML diagrams, but it also looks and feels the same as a MATLAB program that we make. And we have a sensor, which takes as input both the environment and the system state. And that might be weird for, let's say, controls people, but it makes sense to systems engineers. And we actually, even in this diagram, we unify two views. Then a sensor measures the environment. So basically gives you a digital representation of a physical variable, but it also measures the system. It finds an estimated state that the system should adhere to keep moving in the air. A controller then takes this estimated state and applies the correct control actions in order for the dynamics to, say, go from point A to point B without falling from the sky. And this is all actually, if you look at the paper, properly done in category theory, but there is nothing necessarily new about this. We just were able to transcribe a controls model into category theory. The really interesting thing to me is that now we can decompose the behavioral interpretation of the unmanned aerial vehicle by constructing a slice category that contains all design choices. So you can think about this as one design choice, but there's this platonic domain that in this case does exist, and a different designer or a different engineer might have chosen a different one. So the sensor gets decomposed to two inertial measurement units and a processor. Then the controller is a processor, and the little motors that move the aileron and move all these things, and X, Y, and Z basically are the control surfaces. So those two things are decoupled here this way, but they could be actually different. V could be in D. And then F is the airframe, which provides the dynamics. One note here that is really important. If I was a mechanical engineer, I would probably decompose F a lot more than I decompose the software and hardware. But I want to know that everything is here, whatever you want to do. If you want to start with this and then send to a mechanical engineer to decompose to F, you can do that. And that's like really amazing from an engineer's point of view, because that's not really easy to do with current tools. So to me, the main result is this diagram, which describes how we can construct a behavioral algebra between models. That means that every functor is a model in this particular sense. So we start with unlabeled boxes and provide some sort of architectural description of those boxes, how they're connected. And then we have a way of adding the semantics of those boxes, knowing that they will compose, knowing that they're composability, that they have composability. To do this, it required us to reverse engineer the composite behavior of the system categorically and combine these possible decompositions with appropriate hierarchical implementations. This ends up being an object in the pre-image of the functor on the right here. And I think that we can keep extended this diagram to have the requirements. We actually have a preliminary version of this that we hope to show you soon. So if you think about it, if we had this connection with requirements now, if we extended the previous diagram to contain requirements, we could have some contracts or some constraints on our system, and those would actually percolate in some sense within our system function or implementation. And if we think about how we do synthesis in engineering right now, which means you have a model and you can create a system out of your model on Fabric, and we build tools on top of that category theoretically, I believe those constraints could even end up in your code, not just your models. Right now we're restricting in models, but you could imagine that if you have enough tooling, those constraints you started just saying informally in the beginning and formalize them in category theory could end up in the actual implementation of the system, which would have huge implications on how we design safe and secure systems in the future. So this is an image that I basically adapted from the NIST guys, and it shows my view of that picture. I think that categorical semantics should be in the center in the future, and they should, for particularly cyber physical systems, contain all the information we want. So initially, we can have stakeholder requirements, which means basically the people that care about the system, either the person that solicited the system or the people that are designing and analyzing the system. Those people are basically the main people you ask before you design a system, and the main people you go back to in order to evaluate that your system does what you want it to do. But there's no connection between those people and the models, and if we had a common language through category theory, we could actually incorporate not just the stakeholder requirements, but the requirements we can decompose from the models. And also, if we had new data, we could incorporate that as it comes to simulating the system, let's say through hardware in the loop applications. And I think that this is very possible today. If you look at the Julia CatLab implementation, or even if you look at Statebox, I think we're at this point where we can do this. It will just require work. And I also think that we do not actually need to show any of the quote unquote difficult category theory to the end user. I think there needs to be a team of people behind this modeling language that implements these things and understands category theory. But I think the end user should just see stuff like, do not connect these two boxes together because their types don't match. Or if you connect these two boxes together, the emergent behavior might be unsafe, stuff like that. And I think this is very possible. So the future of safety and security coengineering, in my opinion, rests in category theory. So we have in this paper the main model, if you want, the basic model of what a cyber physical system should be categorically. But we can produce a contracts algebra on top of that model, and we can capture a subset of safety requirements, the quantifiable ones. And we can actually model attacker actions over that system model. The problem is, and I've done this individually in my work without category theory, is how do you have, let's say, cybersecurity consequences connected with your contract algebra? I don't know how to do that other than with category theory. Thank you very much. This was my full talk on compositional cyber physical systems modeling.
Thank you very much. Okay, great. Thanks for this talk. I didn't see any questions in the chat, I believe. Anyone with a raised hand?
Yeah, I can ask a question.
Hey. Yep.
Yeah. Could you talk more about how the slice category covers this like hierarchy of designs that are compatible with this design? That seems very powerful.
Yeah, so you still need expert input on what to put in your slice category. That's why I said it's like all the design choices. So if you will, you can include incorrect design choices in your slice category. But the point is that we do have a formal way of going from behavioral interpretation to an actual implementation of the system. Now, what you're asking actually has to do with a contract algebra. How do you make sure that whatever you're adding in your slice category conforms to some restrictions that you have beforehand? So hopefully in the next paper, this is going to be cleared up about how we might be able to do this.
Yeah, this like what you put in the slice category, does that relate to the way I think about it as a Julia programmer is like picking types and functions between those types such that type checking is correctness checking. That if the types work out, then the program is correct. That
Right,
is
so
like
you can think the same thing actually about the design of cyber-physical systems.
Mhm.
And what do I mean by that is that you have types. When you're saying that my sensor gives me, let's say, altitude, you know what altitude, what the type of altitude is, right? So in the next paper, we're actually going to add types to this model as they go within the boxes at the implementational level, not at the behavioral level. But what happens is it actually ends up being the same types of types, if you will. So they work out, which I didn't expect, but Christina, I think, did expect that. So it was pretty cool to see that.
cool. Thank you very much. Excellent.
All right.
talk.
Thanks. There's a question from Zinovid Diskin. Please go ahead.
You're muted. I can't hear you.
Sorry, 1 second.
Yeah, I can hear you now.
Can you hear me now?
Yes.
Okay. So first remark that it's ambitious program. I am afraid it's more complex than you think, but I would say you can succeed. Yeah, because it looks like a right approach. So it sounds very, how to say, encouraging what you described. I also believe that it's a way to go. And another remark is technical. When you rebuild that initial model into 3-stage model, requirements, then functions, then implementation. I believe that requirements is not a stage. That is, you have functions and implementation, and requirements should be put together with behavior and architecture, just constraints for behavior, right? That is
correct. It depends how you see it. If you were a systems engineer, you would certainly consider requirements engineering a different stage.
Yes, I know, but actually requirements make sense if you assign them to functions, right?
That eventually, yes, but you can start with pure requirements as well. But yes, I agree with you. That's why if you saw in the picture with the wiring diagram, I kind of connected the behavioral version of the wiring diagram with the requirements. That's why I did that, because I agree with you in some level.
Yes, yeah. If we want to rebuild it as formally sound, yes, then requirement should go inside behavior architecture. And those that we have is just decomposition. We start with high-level requirements and then decompose, which actually many experienced safety experts, they say all that you need to do just to decompose safety requirements.
Okay, thank you, Zinovi. There's not much time and there's another question, so I'd like to give another person a chance as well. Maybe you can continue on Sulip. Fabrizio, please go ahead.
Yeah, I just had a very quick question. I understand that this formalism can be useful to engineers because it implements stuff that engineers don't have at the moment, or they have it and it's underwavy. But regarding implementations, my question is, for instance, at Statebox, we are trying to implement all this sort of stuff in a formally verified way, so using Idris. The question is, how much do engineers care about having a formally verified implementation? Is this useful, or people like don't give a shit and they just want some
people actually probably care about formal verification engineering more than any other field I know about. So if you look at MathWorks, they are actually trying, that's the problem, is that they're trying to do the same thing without category theory, and it just ends up being a mess. So they have Simulink, which can decompose down, let's say, to an FPGA, which is a way to reprogram basically digitally gates, NAND gates and stuff like that. And that's a very big issue for engineers. How do you formally verify your actual implementation? Not the model of the implementation, your actual implementation.
Okay, so I don't have to drop Idris for JavaScript. That's good to know.
No, and actually I'm thinking that what needs to happen is that somehow either with Julia or Idris or whatever is to connect to hardware description languages. If you manage to do that, that's going to be revolutionary in engineering.
We have some projects to do Idris supervised assemblage of FPGAs and microchips, but maybe that's for another.
That's amazing. Please keep working on that.
Yeah, that would be very useful.
All right. Thanks. So I think that was all the questions. A really interesting discussion, and I'm sure it will continue on Zulip. So let's have a break now, and we continue again at 10 past. So in 4 minutes, basically. Oh, and sorry, I meant to say thanks again to Georgios for his talk. One last thanks, if everyone is still here.